Today we're on worksheet 27 of the AP Chemistry Chapter 8 and 9 packet, and we're going to be taking a look at potential energy versus internuclear distance graphs. What we're looking at is the proximity of two hydrogen atoms together. How close will they be when they bond? So as you know, each hydrogen has one proton in the middle. And so if we represent that with a plus sign inside the atom, we will see that if they're so far apart, okay, like this far apart, there's going to be very little potential energy between the two. They're too far apart to bond, okay? As we get closer and closer and closer, what's going to happen is the potential energy decreases. A low potential energy means something is more stable. It's kind of like gravity, but not really, but gravity is sort of like an analogy. So if I have this, just this little ball right here, and I let go of it, it has a lot of potential energy, but it's going to be more stable at a lower gravitational position. Okay, so this has nothing to do with gravity, but it's the same concept. The lower your energy, the more stable you are. So in this diagram, you could see that as these two nuclei get closer and closer and closer together, they're going to become more and more stable. And you'll see that the diagram is going to have its minimum right at this spot right here. So what that means is the most stable energy they're going to have is down here. So this energy right here is how much energy there is potentially between these two when they're bonded. So if we use this model, and again, it's not going to look the same because they look farther apart here, but just to use the analogy of the bond, when they're at the perfect distance from one another, then they're going to have the lowest potential energy, and that's when they have their single bond. Now, what happens if you push them even closer together? So it's not really pictured in this diagram, but if your pluses are too close together, what's going to happen is they're going to repel each other because the nuclei are too close. And that's where you're getting this part of the diagram that increases very much so right here. Okay, that means that there's now, it's very unstable because the nuclei are too close together. So we found the perfect spot to be right where we labeled the bottom of the graph, and that distance is going to be the bond energy. So if we take a look at this period, this bond energy table, and we look for hydrogen H2, and we see that there are 432 kilojoules per mole for the bond energy, then that's how much energy it would take to break this bond, 432 kilojoules per mole. Okay. Now, what we want to do is not only understand hydrogen, but we want to also contrast that with nitrogen and oxygen, which are also diatomic elements. So if we draw the Lewis structure for these, we will see that hydrogen, of course, has just H2 with a single bond. Sorry, I meant to draw this single bond. Okay, if you drew the Lewis structures for oxygen and for nitrogen, you would find out that oxygen is going to have a double bond with two lone pairs. Sorry, I keep hitting that. And then the nitrogen is going to have a triple bond with one lone pair. What we want to do is we want to contrast these two, okay? So the first thing we can do is think about the bond energy. All right, now looking at these Lewis structures, you could see that we're contrasting a single, a double, and a triple bond. So you're going to guess that the strongest bond is going to be the triple bond, which is the nitrogen. So if that's the case, then the nitrogen is going to come down to a lower level here. It's going to have a longer arrow down like this to show that it has a higher bond energy. Okay, and then if we contrast that with the oxygen, that would probably be not as much energy as the nitrogen because it's a double, but more than the hydrogen because the hydrogen's a single. So we would guess that maybe the oxygen would come maybe this far down. Okay, now the next thing we have to determine is what kind of bond length are we going to have, which is called the internuclear distance, which we can see labeled right over here. This is internuclear distance. So how far over? So again, the hydrogen came this far over for the nuclear distance. So that's going to be, let's say, this. Now we want to think about how is that going to compare with oxygen and with nitrogen. So if you go back to our periodic table, remember we learned about the trends that hydrogen ends in 1s, whereas the nitrogen and nitrogen and oxygen, they end in 2p. So this ends in 2p, and the nitrogen also ends in 2p. Now, what we have learned in the past is that as you go to the upper right, you're going to be a smaller size. And remember that as we move across, the oxygen is going to be smaller because although they end in the same level, oxygen has more protons, more attractions, so a smaller size. So you would predict that oxygen is a smaller size than nitrogen. So it would seem that the nitrogen is going to be farther away from one another because they're bigger. However, there's an exception here because, as we just said, there's a triple bond for the nitrogen. So because the nitrogen has a triple bond right over here, it's actually going to pull the nuclei closer together because N and O are really not that different. Okay, they're not that different in their sizes right here, but the triple bond is going to pull it closer. So if we take a look at these models, you can kind of see it. Okay, here's a triple bond for nitrogen. And if you look at oxygen, you could see if I hold it right here that the oxygen is longer than the triple bonded nitrogen. However, the hydrogen, and the models do capture this nicely, the hydrogen is shorter than the oxygen's double because hydrogen, remember, only ends in a 1s and oxygen ends in a 2p. So what we're going to find out is that nitrogen is going to be the shortest length after the hydrogen. Okay, so after the hydrogen is going to be the nitrogen. So let's say that's going to come to, somewhere over here, and then the oxygen is going to be a little bit longer, and it'll be, the longest one out of all these. So if we wanted to draw this, we're going to do it, and I have it drawn already just to make it a little easier to see. Okay, so here's how it's going to look. The hydrogen, one more time, goes this far down, and that was 432 kilojoules. The nitrogen is going to go farther down like this. And if you look at this chart right here, you'll see that nitrogen has a bond energy triple bond of 941. All right, and let's contrast that while we're here with the oxygen. The oxygen double is 495. So 495 and 941. So 941 is the nitrogen, and 495 is the oxygen. So this is going to be right here, 495. Then, as we said before, the hydrogen is going to be the shortest because it ends in a 1s. Then out of nitrogen and oxygen, although the nitrogen is a slightly larger atom, because of the triple bond, it will actually be a shorter internuclear distance, and the oxygen will be a slightly longer internuclear distance. So hopefully that helps you understand what this diagram is. And listen, even if you had no idea whatsoever what this diagram meant, clearly, if you had to pick a point that meant something, it would be that point. So just knowing that alone is going to help you answer a question on any kind of test along those lines. But hopefully this made sense to you, and you can understand how this diagram works. Try to get back here to pause this.